Okay, so our next speaker is Bodan Arsovski. I'm not pronouncing it right. He will speak about non-Archimedean harmonic analysis.
Hi everyone. So the topic of my talk appears to be somewhat generic. It's about harmonic analysis over non-Archimedean local fields. However, my intention is rather more specific. I'm going to discuss several open problems that are hopefully on the horizon. And my intention is to motivate these problems. So to that end, I will have to begin with some history. So I have to start at the beginning, and I will only mention that the history begins with Andre Bill's development of representation theory and Fourier analysis over locally compact abelian groups. Of course, I mean, it was pivotal to the history of number theory and representation theory and so on. However, I would now the specific direction of the influence I want to discuss is that in part motivated by applications to representation theory. By the 1960s, it became quite popular to attempt to examine and translate the cutting-edge Euclidean harmonic analysis questions to the setting of non-Archimedean local fields. From the point of view of analysis, the rationale was simple. The ultrametric ought to simplify things in a setting that is close enough to the Euclidean setting that many of the fundamental concepts in classical analysis carry through. For instance, the various transforms, the various special functions which show up in representation theory, the theorems in Fourier series, and so on. For instance, at the time in the 60s, harmonic analysis, Euclidean harmonic analysis, largely centered around Calderon-Zygmunt theory, which is roughly the theory of certain singular operators like such, which have a kernel which is singular on the diagonal x equals y, and it satisfies some other technical properties. And this theory stemmed from the seminal paper from 1952 by Calderon and Zygmunt on certain singular operators. And so people examined this theory and transferred most of the key concepts, including the ideas from the Calderon and Zygmunt's paper, to the local field setting. Now, that was the 60s, and beginning in the early 70s, Euclidean harmonic analysis began coalescing around a group of what proved to be interrelated conjectures, which I will list as follows. So the most general one is the local smoothing conjecture for the wave equation. There is the Bochner-Ritz conjecture, the Fourier restriction conjecture, and the Kakeya conjecture, which I will split into the Kakeya maximum conjecture, which is about operators, and the Kakeya set conjecture, which is about sets. These conjectures form a tower of implications, and they are a blend of folklore and being able to be traced to a specific point in time. For instance, even though the two-dimensional version of the Kakeya maximal conjecture was already proved in the 70s, it was not, the full general version was not formulated in print, as far as I'm aware, until a 91 paper by Jean Bourgain. And the local smoothing conjecture is due to Christopher Soggy in 91. And the Fourier restriction conjecture is due to Elias Stein. And the Kakeya set conjecture is essentially folklore. Now, the study of the connections between these conjectures began in around 1971 with Charles Pfefferman. Charles Pfefferman proved that the Kakeya set conjecture, if it had a counterexample, it would disprove the Bochner-Ritz conjecture. And he also used Kakeya sets to non-constructions of Kakeya sets to disprove the closely related ball multiplier conjecture. It was subsequently proved by Terence Tao that the Bochner-Ritz conjecture implies the Fourier restriction conjecture. And these problems turn out to be related, and they also turn out to connect to surprisingly diverse areas of mathematics, ranging from partial differential equations, which motivated, of course, the local smoothing conjecture and so on, to analytic number theory, and to combinatorics. I'm just going to give two instances of this. I'll discuss partial differential equations shortly, but I will give two instances of unexpected applications of this of the work that went into these conjectures. The first one is that the first case of the Green-Tau theorem, so the case about three-term arithmetic progressions, was proved by Ben Green via what he called a restriction theorem for the primes because of its similarity with the Fourier restriction conjecture as applied to the alternative settings of primes. And I have to mention probably the most significant technique that came out of came out of this to be applied to other areas of mathematics is decoupling due to Jean Bourgain. Now, the local smoothing conjecture appears to be the most difficult one. Even in 2 dimensions, it was only proved around 4 years ago by Larry Good, Hong Wang, and Ruxian Zhang, whereas the other conjectures have been known in 2 dimensions since the 70s. So in dimension 3 and above, they are all open. So I want to focus on the Fourier restriction conjecture. And I will briefly state it because I think it's the easiest one to motivate. So it concerns, suppose that E is some submanifold of Rn, which has dimension n-1. And the question amounts to this, for which values of S and T is the restriction of the Fourier transform 2E a bounded operator if we equip the domain with the LS norm and the codomain with the LT norm. Now, important cases of this, well, the prediction for these ranges depends, of course, on the submanifold E. And important cases that come from partial differential equations, specifically the Helmholtz equation, the Schrödinger equation, and the wave equation, are the sphere, the paraboloid, and the cone. And we have predictions, which is essentially the conjecture by Liechtenstein about the ranges of S and T for which the operator is bounded. The restriction conjecture is known up to dimension 5 for the cone and up to dimension 2 for the sphere and paraboloid, and the sphere and paraboloid versions imply the Kakeya maximal conjecture. Now, I will not fully discuss the Kakeya maximal conjecture other than say that it is similarly a question about the boundedness of a certain operator. The reason I will not discuss it is because it has a very elegant special case, which is obtained by evaluating the operator in question to the characteristic function of a Kakeya set. So what we obtain by doing so is the Kakeya set conjecture, which has a very simple statement. Suppose we have a compact subset of Rn, and suppose that compact subset contains a line segment in every direction. Then we will call such a set a Kakeya set, and the Kakeya set conjecture states that such a set must have full dimension n. One reason why this is interesting is because we can construct rather small Kakeya sets, i.e. of Lebesgue measure 0. What the Kakeya set conjecture states is that nevertheless, there is a lower bound on how small they can get in terms of the Hausdorff dimension. Now the Kakeya set, one of the reasons why it is interesting is because it's a special case which captures the combinatorial essence of the problems at hand. In particular, we can summarize this combinatorial essence as being about the incidence geometry of thin tubes. Just to elaborate on that, if we fix a small scale epsilon, and we thicken the Kakeya set by epsilon, what we end up considering, rather than a set containing a unit line segment in every direction, is just a finite collection of epsilon tubes pointing in an epsilon mesh of directions, which, and the definition of these terms is exactly what one would expect it to be. And this is a discrete problem, and it is about the incidence geometry of how tubes can intersect. There is one crucial difference that happens between this incidence geometry in Euclidean space compared to related problems that are combinatorial, such as the joints problem and so on. And that is that tubes, unlike lines which typically intersect in one point, can have a very substantial intersection if they intersect at a small angle. So because the Kakeya conjecture asks about packing these epsilon tubes as tightly as possible, this phenomenon of the tubes being able to have large intersection results in measure 0 Kakeya sets and the difficulties of the problem. So this brings me back to the p-adic numbers. And the reason that p-adic numbers are a good model for for these problems is because this incidence geometry of thin tubes is translated in a very similar fashion over QP. So historically in the 90s, Michael Cowling first suggested considering and attempting to translate this question over the setting of QP. And this program was carried through by James Wright, who noticed that several things. Well, he managed to prove that the restriction conjecture has a satisfactory model over the p-adic numbers, and that most of the method known at the time and the known results carry through, not only with the same theorems, but the same bounds for the schema asymptotics for the norms of the operators in question, because these are conjectures about certain operators. And he also showed that the Kakeya conjecture has a satisfactory model of over the p-adic numbers. That moreover, the known results, such as the fact that the tower of implications, the fact that restriction implies Kakeya, is also translated in the p-adic setting. And he, based on a construction by Thomas Wolff, who constructed measure zero Kakeya sets in the real numbers, he adapted that construction to the p-adic numbers, so that the p-adic numbers also have examples of very small Kakeya sets. And the reason why this analogy between QP and NR exists is because, as I mentioned, the combinatorial essence of the problem is about the incidence geometry of tubes and the way thin tubes behave, in the sense the way they can intersect at a small angle and have substantial intersection, is very similar between R and QP. Right. So that is the history of the problem, and that is the project, at least the dream of it, to address this collection of conjectures in the alternative setting over QP as opposed to the real numbers. Of course, one part of this is to even properly define the top two floors of this tower, which will involve discussing the wave equation. In a way that is consistent with the implications, the tower of implications, in a way that is consistent with what happens with the real numbers. The bottom two I previously proved, and my proposal for what I will hopefully work on this year, staying at IS, is well, the middle floor, specifically the p-adic Fourier restriction conjecture. More specifically, the natural next step is the p-adic restriction for the paraboloid. Now, this talk was structured largely as a survey, and the goal is to motivate these p-adic questions and hopefully make an argument why they might be interesting things to study. So, to that end, let me also add several closing remarks. Now, first of all, I will talk about some more history. So, around the same time that Cowling and Wright considered the p-adic versions of these problems, Thomas Wolff independently suggested working at simpler models over finite fields. Now, these models replace the incidence geometry of tubes with the incidence geometry of lines, so they lose that aspect of the problem, thus making it simpler, however, at a cost. It was initially not clear whether the restriction problem has a satisfactory model over the finite fields in a way that it fits in this hierarchy of implications, i.e. it implies in a natural way the Kakeya conjecture. And this was until a paper by Mockenhaupt and Tal, where they proved that there is indeed such a formulation of the restriction conjecture. And in 2008, Dvir proved the finite field Kakeya conjecture. And this method subsequently became known as the polynomial method. And then Jordan Ellenberg, Richard Oberlin, and Terence Tao used his ideas to settle the Kakeya maximal conjecture for operators. And now the polynomial method has since been adapted from this finite field setting to the Euclidean setting, and some of the best cutting edge partial results on the Euclidean questions in harmonic analysis I mentioned are use adaptations of that method. Now the question is, what was the main goal for studying these model problems at the time? And well, to people who suggested the problems, it was to establish perhaps new ideas in the simplified setting that hopefully could be could reflect back to the Euclidean setting and tell us something new. And indeed, in that taking that perspective, there has been some success because there have been significantly many results in Euclidean setting based on the final field setting. So now I also want to address the fact now what happens with the hierarchy in the finite fields case. Kakeya is largely settled, and we completely understand what happens, but the restriction conjecture is still open. And one might think that this means that if in this simplest setting the restriction conjecture is still open, then it might be out of reach in the setting that looks closer to the real numbers, the p-adics. However, this might not necessarily be the case. Well, the reason behind that is that even though QP is more complicated than FP, the restriction problem over FP is less natural in many aspects than the restriction problem over QP, in the sense that the paper by Mokenhaupt is quite difficult and involved, and the implication restriction to Kakeya is not direct. There is a convoluted chain of implications that prove a similar statement that restriction lies above Kakeya in this hierarchy of implications, but it's not a direct implication like in the Euclidean setting. So the relation between restriction and Kakeya, and as well the relation between restriction and Euclidean restriction, are not as clear in the finite field setting. So it might well happen that the p-adic setting is being more natural, proves to be an easier setting to discuss the restriction conjecture, and it may be the first setting where it is proved. So I guess this slide is just there to comfort anyone who wishes to attempt working on the p-adic problem, knowing that the finite field case is still open. And finally, all of these settings discuss analogous settings for the problem, but analogy is not proof. And it might well happen that the Euclidean conjectures are in fact false. I mean, my understanding is that there is not 100% consensus that these conjectures are valid. And in fact, some people may suspect that even the Kakeya set conjecture could have a counterexample. And in such a scenario, I mean, the reason why one might want to study alternative settings is first, the obvious philosophical one. I mean, if it's not true in the Euclidean case, why is it true in these other cases? But also more directly, because we get a hint for how to proceed searching for a counterexample. So when Dvir in 2008 proved the finite field Kakeya conjecture, Terrestau wrote a blog post saying that what it does, this essentially rules out any algebraically constructed counterexample to the Euclidean Kakeya set conjecture, because any counterexample that could be described with algebraic equations could be ostensibly transferred to the finite field setting. Similarly, by looking at settings that are closer to the real, such as the p-adics, we can conclude, for instance, that any potential counterexample to the Kakeya set conjecture must in some fundamental way rely on the Archimedean property of the real numbers. And this might provide some small hint to anyone attempting to search for a counterexample. So I'm not sure what the time is, but I was
a little bit over time.
Okay.
So, yeah. Okay, maybe say one last sentence. Okay. I think we, for the second session, we only have one lecture, so we can go a little longer here, about 5 minutes with that. So any questions? I have a question. Bodan pointed out in a paper that seems to be really not looked at much, that the conjecture of Montgomery about the Dirichlet polynomials implies a Kakeya in the Archimedean case. I wonder what the p-adic analog of that is. It might be quite informative. Because the Montgomery conjecture is not clear whether to believe it.
I think that conjecture is a lot more general, and my impression is that also.
The question is, could you formulate a p-adic version of that and see what that is? Because that's an implication which.
Right. So yeah, that is probably an interesting open problem.
I'm just asking.
It might be quite interesting to formulate a p-adic version of that, which would imply the p-adic.
Yeah.
Okay. Yeah.
Which you know is true. All right, so those who want to do real analysis, as the move. Anyway, so I think we can end there. Thanks for you again.